Now let's see this question. This question came in GATE 2015 for 1 mark. The question is, what are the worst case complexities for insertion and deletion of a key in a binary search tree? So they have given 4 options. We have to find the worst case complexities for insertion and deletion. So let's firstly understand in a binary search tree how insertion and deletion will happen. Okay, so let's say any binary search tree, and here it can be something like 1, 2, 3, 4, 5, something like that. Okay, so this is a binary search tree. We have to perform insertion and deletion. Okay, so let's keep it 6. I will make you understand why, because I will try to insert 5, then we will understand how. So if we are trying to insert, then what is going to happen whenever we are trying to insert anything, then basically we start from root, and whatever we are going to insert, if that is bigger than root, then we'll go towards the right. If that is smaller than root, then we go towards left, and we do that recursively till we find the proper place to insert, and then we insert it, right? So if we have to insert something like 3.5 here, then what is going to happen? We are going 3.5 is less than 4, we go here, then it is greater than 2, it is here, and then it is greater than 3, and that's why it is going to be the right child of 3. So 3.5, if something like that is there, then that is going to be inserted here. What about something, let's say 5 we have to insert, then 5 is greater than 4, so we have to go right. Again 6, it is less than 6, so it is going to be to left, but in left there is nothing there, so we can insert a node which is 5 here. Okay, so that is how insertion and deletion insertion is going to happen. Now we will understand deletion. Okay, so how deletion is going to happen? The rule for deletion in a binary search tree is that we search the proper root, proper node starting from the root, and we go to till that element, and after that, if that is a leaf node, then we don't have to do anything, we simply pluck it off, and that is the deletion. If that is an internal node, then there is a way how to do that. So my point is that if you have to delete, let's say 3, then you simply search for 3. Where is 3? Start from the root, come here, because it's smaller than 4, but 3 is greater than 2, so you go right and you find it. And if you find it is a leaf node, then you simply plug it off, you delete this, and that is done. But what if that is not a root node, that is not a leaf node, sorry, it is a internal node? Then what is going to happen? So let's keep this 3 as it is. Now if something is an internal node, let's say we want to delete 2, or we want to delete 4, if anything is an internal node, then the algorithm is something like that we have 2 ways basically. So we can find the maximum in the left subtree, or we can find the minimum in the right subtree and replace it with that particular internal node. So let's say we are following the pattern where we want to, when we are deleting that node, then we are replacing it with the maximum of left subtree. So if we want to delete 4, then we will find the maximum in the left subtree, and what is the algorithm for that? We go towards the left subtree, and after that we keep on going right until we reach the rightmost leaf, and that is our maximum in that left subtree. So here 3 is going to be the maximum, and then we simply delete this and put, instead of, we delete 4 and then we pluck this 3 from here and put it here. So our new, after deletion, our new binary search tree will be something like this. Right? Pretty simple. Okay, so these are the two ways of insertion and deletion. Now we just have to understand that what is the time complexity, worst case complexity for this to happen. So in worst case, while we are trying to insert anything, we might have to go all the way till the depth, all the entire height. So if the height is basically h, then order h is going to be the insertion time. Similarly, if we are going to delete, then there also it might happen that firstly we have to search that also might be order h. But if it is a leaf node, then it will be order h. If it is not a leaf node, it is an internal node, still you might have to find the maximum of the left subtree, and for that again you might have to go all the way till the entire depth. So whatever is the height, that might be again the complexity in worst case. So for insertion as well as deletion, both the time taken is going to be order h. Okay, so my point is that now we have to, for if there are n nodes, if there are n keys in a binary search tree, then what is the worst case height going to be? That is our worst case complexity, okay, because everything is order h. So you might be tempted to think that okay, so if let's say n elements are there, then log n is going to be the height of binary search tree, but it is not the case, because because when you're talking about a log n type of binary search tree, its height is log n. If n nodes are there and its height is log n, then that can only happen when sort of the height is sort of the binary search tree is full binary search tree, sort of like this, then only it is going to happen. But technically this is also a binary search tree, right? Simply this is also a binary search tree, because the properties of a binary tree is satisfied. What is the property of binary search tree? That no node should have more than 2 children. So it can have a maximum of 2 children. So either it can have no children like here, or it can have one child like here, okay, and it can have 2 child also like this, but we are trying to maximize the height, right? So we will not consider this, and we will see that okay, what is the worst case, like maximum height, what is the maximum height that can happen? So basically maximum height for n nodes can be n minus 1, which is basically order n. Okay, so basically h is equal to order n. That is what I wanted to prove. But we already understood that our insertion and deletion algorithm takes order h time. But what is h? H is order n. So basically our insertion and deletion algorithm in worst case will take order n time. Okay, so and obviously it will be omega n also, right? Because we cannot do better than that. So it is bounded, strictly bounded by n. So basically it is theta n. What I wanted to say, that overall it is theta n, because it is strictly bounded by the height, which is order n. Okay, so theta n for both insertion and deletion. B is the correct answer.